let's move on into induction machines. So induction machines are very different than synchronous machines. And so we'll talk a little bit about the basic operation of them. We'll talk about, the benefits, the advantages of induction machines. You see a lot of induction motors out there, especially smaller motors. And then ultimately we'll talk about single-phase induction machines, because there are some unique challenges associated with them. So an induction machine operates on the basis of an interaction of induced rotor currents and the air gap field. So that's be the gap between the stator and the rotor. So aim in the air gap, well, really it's the gap between the stator and the rotor. Has to be there, otherwise you'd have the stator, basically fixed to the rotor fixed to the stator, and the thing wouldn't turn. So when we talk about air gap, we're really talking about, if you have, I'll just do a quick, if this is your stator here, and this is your rotor here, it rotates inside the stator. Square that up so it's nice and symmetrical. And I'm going to make that, that's what this is for. I've never actually filled anything in before. There we go. So the rotor would be blue there, and the rotor's rotating at some, some omega. So we'll make it go like this way. Oops, hold on. So it's rotating at some omega of the machine, and the air gap is this area between the stator and the rotor. Of course, the rotor is supported on either end by a shaft that rides on a bearing. But if this is your stator with your stator windings, and this is your rotor, there's an air gap between them, has to be there. In other words, in order for it to rotate, can't be fixed to the stator. Does that make sense? So when we talk about air gap power and things like that, we're really talking about the power that, is induced in the rotor, from the stator in a induction machine. So that'll become a little bit more apparent as we talk about power flows and things like that. But that's what the air gap is, and it's necessary in the construction of a motor for it to even function. Okay. You bet. Let's see. So where were we here? So we have induced currents into the rotor that cross the air gap from the stator. And if the rotor is allowed to run under the torque developed by this interaction, the machine will operate as an induction motor. So in other words, you're going to develop a torque in that rotor that then you can drive loads with and things like that. Now, if the rotor were driven by external force and driven beyond the speed of the stator's rotating magnetic field, then it would deliver electrical power and would operate as a generator. Induction generator. So it is possible to use an induction machine as either a motor or a generator, very similar to the dual purpose or dual capacity of a synchronous machine. But it's not common because it's harder to control the output signal of an induction generator because there's slip. So the rotational speed of the rotor and the stator magnetic field in the case of an induction motor are different. The rotor is turning slower than the stator magnetic field in order to get relative motion. It all works in relative motion. That same thing applies. So if you were rotating the rotor by some external force, you'd have to turn it at higher than the frequency you wanted the signal to be developed, and it's hard to directly control that. In synchronous machines, remember, they're exactly the same rotational speed. So if I'm trying to get 60 hertz out, I turn that rotor at a precise speed and I get the 60 hertz. They're rotating at the same angular frequency. Induction machines aren't that way. Therefore, it's not common to have induction generators, just harder to control the output. But they do exist in a couple of different environments, and usually there's some kind of circuitry to create. We're kind of like a VFD in reverse, where you can control through digital to analog circuitry a specific output. So we'll focus predominantly on induction motors in this class because that's the most common thing out there.